Welcome back to Unit 1 of our course, The New Perspective. We are now on Lecture 8. Now, what we did in the last 3 lectures, I guess, we started from this expression for conductance we had and applied it first to the ballistic limit, then to the diffusive limit, and then we said you could all connect it all together and write G as sigma A over L plus lambda. And again, I noticed there's a little mistake here. This should have been sigma A, see, and that's equal to GB lambda. And as I mentioned, this is this new perspective we are talking about, where the fundamental material parameter is this ballistic conductance. And the conductivity times area, which should have been here, is the mean free, is this ballistic conductance times the mean free path, this lambda, which we defined as the ratio of this diffusion coefficient to the average velocity. So what we'll do in this lecture is, we'll talk a little more about what these two quantities are, this d bar and v bar. You see the v bar that entered the ballistic conductance, the d bar that entered the conductivity, and this lambda, which is this ratio of d bar to v bar. Because this bar indicates there is this averaging involved here. So let's start with the simplest case, you see, that is a 1D conductor. So in 1D, and we are talking of, remember, elastic transport, so we are talking of electrons with a certain energy. So a certain energy corresponds to a certain velocity. But the velocity could be either in the positive z direction or in the negative z direction. So it could have one of two values, plus v and minus v. No other value, because as I said, we are considering electrons with a single energy. As you know, in this elastic model, we can think of one energy at a time and then do an integral over energy. So you're considering one energy, one particular value of velocity, but it can be plus or minus. Now, so what is the average value? Well, average value of v bar is got two possible values, plus v and minus v. So basically the average value is just v. What about the diffusion coefficient? Well, that's Vz squared tau. Again, two possible values, each is equal to V squared tau. So you can just write that. And then what we call lambda is this 2d over V, 2d bar over V bar. And when you put that in, you get 2V tau. Now the 2 might puzzle you a little bit, because thinking about it, you see this V is the velocity, tau is the mean free time. So you say, well, velocity times mean free time, that should be the mean free path. Now, why a 2 in here? And the thing is that this is the mean free path for backscattering. So the way it is here's an electron going along, and every time it hits something, it turns, changes its direction a little bit, and tau tells you how often it hits something. Now, the thing is that when it hits something, the direction changes, and we are assuming that the process is isotropic. So you are going this way, you might scatter to that direction or to that direction. But what we are really interested in this context is whether it has completely turned around, whether it has backscattered. Because as long as you're still going straight, the point is you're still headed in the right direction. You're still in a northbound lane, so to speak. So of all the scattering processes, there will actually be half which will kind of keep you moving in the same direction, and the other half which will turn you around. And so the average time for actually getting turned around is not tau, but 2 tau. And so this lambda, 2 tau times v, is, you could call the mean free path for backscattering. Now the exact factor that appears here, that as you'll see, will be different in different dimensions. That right now we are talking about a 1D transport. Next we'll talk about 2D, where you can go around in a circle. And then we'll talk about 3D. And that exact numerical factor will change a little bit. So let's do 2D. So in 2 dimensions, of course, we have the z direction, which is the direction between source and drain. And then you have electron velocity, which can be at any angle, say that the angle theta. So how would you average it? You want the average velocity. So we want Vz So Vz means the component along z, which is v cosine theta. So I put a v cosine theta there. That's the absolute value of v cosine theta. And you have to integrate from minus pi to plus pi. Now to get the average value, of course, you should also divide it by integral d theta. So one way to check is, let's say the quantity you are averaging was not this, but something with a constant value, say 1. Then you see after you average, you should still get back 1. Or if you are averaging, say 2, you should get back 2. So if you divide it by the same thing here, but without that, that ensures that a constant thing will average to the constant value itself. So this is the average value then. And what you could then do is take out this absolute value kind of by integrating only from minus half pi to plus half pi. Because the idea is that this is the range where the cosine is positive. If you look at the range that we left out, that's where the cosine is negative. And in that range, when you take the absolute value, of course, you'd get back positive. And so what we could do is just integrate over minus half pi to plus half pi. Or I guess you could have written a 2 here, which is like you're multiplying what you get from here by 2, because the part you left out will give you exactly the same thing. But then you'd also have a 2 here, so I've just dropped the 2. And this is now a straightforward integral, and what you'd get is 2v over pi. So for in 2D then, that's the average velocity you should use. Note this extra factor of 2 over pi. What about the diffusion coefficient? Well, now the average that is involved is Vz square tau, that quantity. What's Vz square? Well, that's V square cosine square theta. So I've pulled the V square out of the integral and left the cosine square theta in there. So what you have to do is integrate d theta cosine square theta divided by d theta. And again, this is a straightforward integral, and the answer you'd get is V square tau divided by 2. Now for the 3D case, which is the most complicated, I guess, mathematically. Here the way you think of it is, you have these two angles. One angle which is with respect to the z-axis, and then you project it down to the xy plane and look at the angle with the x-axis. So there's these two angles, theta and phi, which define a particular direction in 3D. Now, if you're not familiar with it, it takes a little time to get used to this. So what I'll do is, I'll say, refer you to standard texts, where people find, say, the surface area of a sphere. As you know, if you had a sphere whose radius is r, the surface area is 4 pi r square. How would you find that? Well, usually what you do is do this integral. And as I said, if you haven't seen this before, then this is not meant to be obvious at all. But I'm just saying, this is how people normally find the area of a sphere. This is how you define the solid angle. It's d phi and sine theta d theta. And then when you integrate all this, you get 4 pi. You get 2 pi from here and another 2 from there. That's how you get 4 pi. And that's how you get the area of a surface area of a sphere, 4 pi r squared. Now what we need though is just this part, because that kind of tells us how to integrate over angle. In 2D it was simple, it was just integral d theta. But in 3D you need this solid angle here. So you have to do this integral. And so when you write down the average velocity, you have to take v cosine theta like before, because we want Vz, and Vz is v cosine theta. So that's the v cosine theta, but you have to average over this solid angle. And again, the same issue. What you want to do is, this cosine theta is positive for parts of it and negative for parts of it. What you want to do is just keep the parts that are positive, because the negative will give you exactly the same thing. So if you take it out from both numerator and denominator, you're fine. Now you can do this integral, and that will give you half of v. Now if you want the diffusion coefficient, again same story. Now it's v square cosine square theta times tau. The v square tau is pulled out. So you have cosine square theta, which has to be integrated over the solid angle. And this will give you v square tau over 3. So we have kind of gone through this thing then for 1D, 2D, and 3D. So if you collect all those results together, you see, what you'd have is average value of velocity. In 1D, it's just v. 2D is there's a 2 over pi. 3D, there's a factor of half. For diffusion coefficient, actually the result is quite simple. It's v squared tau. 1D is 1, 2D is half, 3D is 1/3. So it's like 1 divided by the number of dimensions. So in fact, there's actually a simple argument that can be used to get that result without doing all these integrals, but I won't go into that. I wanted to do everything in a straightforward parallel way. So you get these averages directly. And now if you look at the way we define lambda as 2 times the diffusion coefficient over velocity, you can see what you'll get. When you divide this by this, of course v squared tau divided by v, that's what gets you the v tau. And the numerical factor in each case you can try out. It's like 2 times this divided by that. So it's, for 1D you get 2, like we had discussed before. That's this mean free path for backscattering that I had mentioned. 2 times this is 1 divided by 2 over pi. That's what gives you pi over 2. 2 times this is 2/3 divided by half. That's what gives you the 4/3. So the mean free path, the way we have defined it, the one that leads to this simple expression as L plus lambda, that mean free path then is v times tau, which is what you normally might think as mean free path, but times a certain factor that depends on what the dimensionality of your conductor. It's always bigger than 1. That's because what we're really talking about is this mean free path for backscattering. And so tau is the mean free time for scattering, but then only a small fraction, only a fraction of all the scattering processes involve backscattering, where you actually turn around. And so the factor here is always bigger than 1. In 1D it's 2. In 2D it's half pi, which is like 1.6 or so. And here in 3D it's 4/3, which is like 1.3. So what we'll do next is, I guess, this kind of completes this new perspective that we are talking about. And what I want to do in the next lecture is talk a little bit about the standard perspective, the Drude formula, and how this relates to that. Thank you.